Welcome. So, continuing with our study of IJK notation for vectors, this question says, given a displacement vector 2I minus 4j plus 5k meters, determine the magnitude of this displacement. We want to know how long the path is. We want the numerical value. So let's, as an aside, let's begin by a bit of visualization. So I have my three principal axes, my x, y, and z, which is my I, j, and k. And this is 2 units along the x-axis. So let's do 1, 2. So I have there's my 2i. And then I have minus 4j. Minus is pointing downwards. So there's 1 unit, 2 units, 3 units, 4 units. That will be minus 4j. And then we have plus 5k. And that would be 1 unit, 2 units, 3 units, 4 units, 5 units. So that would be my plus 5k. How can I visualize the vector that this sequence represents? Well, I just complete my diagram. So let's just drop this vertical down. Let's bring this vertical across. That's the back side of my cube. Now imagine, I've got to be a little bit careful with my drawing here. Project parallel to this axis down here, and then bring this vertical down. That's the side of my shape. Just as we have this back edge here, we got a front edge there. And just as we have this bottom side here, we have a bottom side there. Then to complete our diagram, project this across, project this up, and project this. So it looks like a cereal box. And the actual vector that we're interested in starts at the origin and goes all the way down here without that little wiggle on it. It goes like that. That's the actual vector we're trying to find the length of. It's useful to be able to draw these diagrams. It's useful to be able to draw these diagrams. It's not essential, but it is useful. It really does help for the visualization and everything. So this is the I, this is the J, and this is the K. How do we find the numerical value of this? Well, we actually use, if you like, Pythagoras in 3 dimensions. Let's call this vector R, as usual, our resultant of these things. So we're going to say R squared is equal to the square root of, if you like, x squared plus y squared plus z squared. We're used to this in 2 dimensions, but it also works in 3 dimensions. So R squared, I'm sorry, let me go back. R squared is equal to x squared plus y squared plus z squared. So R is equal to the square root of x squared plus y squared plus z squared. So R is equal to, now with the square root, let's be looking up here. So that's plus 2, and we're going to square it. And then we have this addition operator. So let's put our addition operator in. Now this is minus 4. That's an address. That's a value, minus 4. So we put minus 4 in, and we square that. And then we do our addition operator from here. And then we look up here and we go, oh, that's plus 5. So I'm separating between signs which are operators and signs which are part of the address. So this is the square root of 2 2s are 4 plus. Minus 4 times minus 4 is plus 16 plus 5 5s are 25. So R is equal to 20 square root of 45. 7 7s are 49. So it's probably that 6.7. Second square root 45, enter. Yeah, 6.7 is the answer. So this would be 6.7. It's a thing, it's a physical parameter, so it has units, which is meters. Put it in a box. And it's this guy here. So don't be fooled by negative signs. It's not minus 4 squared is not minus 16, it's 16. Just simple math can trip you up. And that's why writing more steps down means that not only will you make fewer mistakes, but you will also be able to catch mistakes easier when you check your work. And there we have it.